Let's talk about one of the most incredible things you own, your eye. I mean, it's this tiny little sphere that somehow takes the world of light and turns it into the vibrant, colorful reality you see every single day. It's just amazing. But have you ever really stopped to think about how it works? How does this small, delicate thing capture everything from a star billions of miles away to the words you're reading right now? It's this beautiful mix of biology and physics, and we're going to get into it. So, to really get it, we're going to go on a little adventure. We're going to follow just one single ray of white light. We'll track its journey as it enters your eye, gets focused into a sharp picture, and then we'll see how that very same ray of light breaks apart to paint the world in all its amazing colors. Okay, first stop on our journey, the eye's incredible mechanics. Seriously, think of it like the most advanced autofocus system you can imagine, one that's constantly adjusting without you even noticing. And the secret sauce behind it all is a process called accommodation.
So, accommodation. It sounds technical, but here's all it means. Your eye has a lens, and it's surrounded by these tiny little muscles called ciliary muscles. When they tense up or relax, they literally squeeze or stretch the lens, changing its shape. And when the shape changes, its focal length changes. This is how your eye makes sure that no matter what you're looking at, near or far, the image lands perfectly sharp on the retina at the very back of your eye.
And check this out, this is so cool. Here you can see it in action. When you're looking at something way out in the distance, those ciliary muscles are totally chilled out, completely relaxed. This lets the lens become thinner, giving it its longest focal length, about 2.5 centimeters. But the second you look at something up close, like your phone, those muscles contract. They squeeze the lens, making it thicker and squishier. This shortens the focal length, pulling that focus point right where it needs to be on your retina. It happens instantly, all day long, just incredible.
Of course, this amazing autofocus system isn't always perfect, and that's where glasses and contacts come in for a lot of us. Vision problems are really just about physics. It all comes down to where that light is being focused inside the eye.
So, let's start with myopia, which you probably know as nearsightedness. If you're nearsighted, you can see things up close just fine, but things far away are a blur. And the reason is pretty simple. The light is being focused too soon. The image forms in front of the retina instead of on it. So by the time the light actually hits the retina, it's already started to spread out again, and that's what makes it look blurry.
Now, the solution for this is just so elegant. You put a biconcative lens, that's one that's thinner in the middle, in front of the eye. What this lens does is it spreads the light rays out just a tiny bit before they even get into your eye. Your eye's lens then does its thing and focuses them, but because the light started out a little wider, the final focus point gets pushed back, landing perfectly on the retina. Boom, a clear image. As such a simple, brilliant fix.
And then you have the exact opposite problem, hypermetropia, or farsightedness. With this, distant things might look okay, but trying to read a book is a real struggle. This happens when the eye's lens isn't bending the light enough, so the focus point would actually be behind the retina if it could go that far. The light hits the retina before it's had a chance to fully come into focus.
And you can probably guess the solution here, right? It's the perfect opposite. To fix farsightedness, we use a biconvex lens, one that's thicker in the middle. This lens gives the light a little head start, bending it inward slightly before it enters the eye. Then your natural lens takes over, and together they pull that focal point forward so it lands precisely on the retina. Problem solved.
Okay, so we've totally figured out how the eye creates a sharp image, but our little light rays journey is far from over. Up until now, we've been thinking of light as just one thing, but as you're about to see, there's a whole hidden world tucked away inside that white light. Just think about it for a second. The light from the sun, or from a lamp, it looks white, right? Kind of colorless. But the world is obviously exploding with color. So where does all that color come from? Well, the secret is locked inside that very same ray of light. And the key to unlocking it is a phenomenon called dispersion. It's what happens when white light passes through something like a glass prism. The light doesn't just bend, it splits apart, revealing a stunning spectrum of colors.
And there they are, all the hidden components of white light. It's the classic rainbow sequence we all learned in school, VIBGYOR. All of these colors were always there, traveling together in that single white ray. The prism just acts like a sorting hat, separating them out so we can see each one on its own.
So why does it split like that? Well, it's all about wavelength. Each color of light has a different wavelength, and this affects how much it slows down and bends when it goes through the prism.
You can think of red light, with its long wavelength, as taking long, easy strides. It gets through with less trouble and bends the least. But violet light, with its super short, choppy wavelength, gets tripped up more and bends the most. This difference in bending is what fans all the colors out into a beautiful spectrum.
All right, now that we get dispersion, we can take this idea out of the lab and see how nature puts it to work on a massive planetary scale, because that little glass prism is just a tiny demonstration of a much, much bigger show.
So, where does nature pull off this same magic trick? Well, the answer is literally all around us. You see it in the sky after a storm, and you even see it in the color of the sky itself on a perfectly clear day. Nature has its own prisms and its own ways of playing with light.
A rainbow is probably the most jaw-dropping example of dispersion. After it rains, the air is full of millions of microscopic water droplets. When sunlight hits one of these droplets, it goes inside and disperses into all its colors, just like in our prism. Then it bounces off the back of the droplet and comes back out, spreading the colors out even more. Each tiny droplet creates a whole rainbow, and when you see millions of them at once, you get that incredible arc in the sky. But dispersion isn't light's only party trick. There's another thing it does, called scattering. This is what happens when light bumps into tiny particles, like the individual atoms and molecules that make up our atmosphere. The particle basically absorbs the light for a split second, and then spits it back out or scatters it in a totally random direction.
And this, right here, is why the sky is blue. The nitrogen and oxygen molecules in our air are just the right size to be really good at scattering short wavelength light, which means blue and violet light. So during the day, blue light gets scattered all over the place, coming at our eyes from every direction, making the whole sky look blue. But at sunset, the sun's light has to travel through way more atmosphere to reach us. On that long trip, most of the blue light gets scattered away from our line of sight, leaving the longer wavelength reds and oranges to make that final journey to our eyes. That's why sunsets are so red.
And we owe a huge part of our understanding of this to the Nobel Prize-winning scientist Sir Stevie Raman. He made the incredible discovery that when light scatters, its frequency can actually change. This discovery, called the Raman effect, was a total game-changer, giving scientists a brand new way to study the very structure of molecules.
So there you have it. From the autofocus inside your eye to the color of a sunset. It's all just the incredible story of light on a journey. And it kind of leaves you with one final, mind-bending thought. Our eyes can only see a tiny, tiny sliver of the full electromagnetic spectrum. If this entire beautiful world is created from just that little band of light, what are we not seeing? What does the world look like in radio waves or X-rays? It's a pretty wild thing to think about. Thanks for joining me on this one.